Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, I think we're going to start now. This afternoon we have guests from UCL, several researchers from UCL. We are very pleased that two students of Jun Wang, who is a professor at UCL, will be giving a presentation. That's Shuai Yuan and Weinan Zhang. Shuai is the doctoral student in the last year of his studies, and Weinan is the second year student. Some of you may have already met Shuai because he recently interviewed for a postdoc position. He talked about his research for around his thesis. But today, both Shuai and Weinan will be talking about algorithms they used for a particular event. It was a competition in real-time bidding for display advertising with IPNU, a competition in 2013. And they had a fantastic accomplishment. They won the first prize, which actually was quite ahead of the second one, about almost 30% in performance, if I remember correctly. So I will let now Shuai start. Shuai, please.
Okay. Right, thank you very much, everyone. I'm Shuai Yuan from University College London, and actually we are trying to build an Earth Science research team, research group within the Department of Computer Science in University College London, led by our supervisor, Dr. Jun Wang, who is absent at the moment. And today, also, my colleague Weinan Zhang is with us. Last time I talked about the optimization problems in supply side in real-time bidding, but now today we are taking a different angle. We are going to talk about the optimization problem from the demand side, especially the bidding algorithms. Today's talk will be split into three parts. The first, we are going to quickly go through the background knowledge about real-time bidding, and by giving an example and by introducing the ecosystem. And then we are going to talk about our experience from last year's IPNU Global Bidding Competition, where we won the first prize, and we have some practical knowledge or experience. And then the third part, we will talk about our theoretical development based on our experience and our solution to that. All right, and the first part is about the background of real-time bidding. For those who you don't familiar with real-time bidding, you have to know that real-time bidding is getting really popular. And how popular is that? In 2014, it is projected to have 4.6 billion US dollars, of total ad spending, and it is projected to have 30% of total display ad spending in 2017. That's a huge number, and that takes a lot of dollars, and it gives a lot of opportunities. Hence, there are a good amount of research effort around this topic, especially in recent years. All right, so it is popular, but so what is real-time bidding anyway? Real-time bidding means every online ad impression can be evaluated, bought, sold, and all individually and all instantaneously. Right? What does it mean? It means instead of buying a bundle of impressions, several thousand impressions together, advertisers are now buying impressions individually. This means they are actually buying users individually, directly. Advertisers usually used to buy impressions based on the website's reputation, right? They negotiate a contract between salespeople, and then they claim that they have to trust the publishers who claim the user behind that the impressions to be having some characteristics. But now they have their own judgment. They can build their own data set to understand the users and to place a bid for every single user. But what does that mean, especially scientifically? It means it challenges buyers to bid for every impression. You see, it's a fundamental thing. It challenges buyers to bid for every impression, to bid for every user based on a variety of attributes, both contextual and behavior attributes. And especially, you have to do that in real time. By in real time, it means you have to return a bid in about 100 milliseconds. This is also a very huge engineering challenge, right? It challenges the other side as well. It challenges sellers or the publishers to dynamically allocate and price impressions to achieve a higher payoff. It also challenges data providers to effectively track and analyze users' online activity and probably trade with each other under some mechanisms. And at last, it also challenges users as well to understand the trade-off of privacy and free services, which I believe many of you are very familiar with. All right? Haven't talked so much. Probably it's better to show you an example what the real-time bidding actually means. Let's take Weinan, for example. Weinan is very interested in computational advertising research, so he visits eMarketers.com regularly. That's his long-term interest. And occasionally, Weinan has some travel demands. For example, he recently checked London hotels for one of his friends. There's no login is required, actually. This represents Weinan's short-term interest. It only happens within some months or within some weeks. After all these events, visiting the websites, Weinan receives relevant ads on Facebook.com. All right? In the middle, you can see there's an ad for an escape, for travel interest. And to the right, you can see there's an ad for eMarketer reports or services. These ads are created based on his interest, both long-term and short-term, not only based on the context of the web page. But wait, there's an extreme case. There's even an ad on our supervisor's homepage when I visited. You see, the ad is actually from Booking.com about hotels. It has nothing to do with the research or with advertising at all. So you see, in this case, the behavior targeting totally dominates the context. Okay? That's the trend, that's the emphasis of the real-time bidding, to understand a user, to bid against the user interest segments. All right? Given all these, you may ask, how actually does it work? It works like this. In the first step, you visit a website, and this website has some ad slot. It will create an ad request and forward this ad request to some exchange. This exchange will forward this bid request to all the advertisers who are willing to participate in the auctions. And advertisers will check the data management platform for user data or their own database for the user interest, and they will create a bid response. After collecting all the bid responses from advertisers, Ad Exchange will hold an auction, normally the second prize auction, and it will select a winner and send the win notice to the advertiser, as well as display the ad of the winner to the user. And at last, the user would probably give some feedback by clicking an ad or navigating around the website, or even ultimately complete a purchase of some product. All right, this completes the circle of real-time bidding, and it is a complex ecosystem, and we have to understand what we are, our position in this ecosystem. All right. The complexity of the ecosystem has a long history. You can see from this figure, which I showed last time in my talk. But now we are more focused in the center part of this ecosystem, where we are participating in ad exchanges, and we are representing advertisers, and we are trying to make sure we can bid optimally. Okay? In this talk, we only talk about bidding, and now let's talk about the bidding. We already seen that for every web page, for every impression you create, an advertiser has to give a bid. All right, that bid is not, it has to consider many different features. It has to consider both contextual and behavior features, as we talked just now. But how actually did that work? Let's go deep into this bidding engine or the bidding algorithm to see how it works in this talk. All right. Firstly, I'd like to share our computation experience, which in turn inspired us of the theoretical study of the third part. The competition was held in 2013 and was split into 3 seasons. We participated in the second and the third season, and we won the first place of the third season. And by the way, we won the fourth of the second season. I can't remember precisely, but it's a gradual progress. This competition was held by a Chinese DSP, demand-side platform company called IPU. The demand-side platform refers to the technology provider for the advertisers, which enables them to participate in the real-time bidding, which ultimately gives them the power to return a bid for every ad impression. All right? And IPU claims to be the biggest DSP provider in China, in Chinese advertising market. So this is quite a formal competition. The task for this competition is quite simple, actually. It's very easy to understand. It's basically you receive bid requests, and you have to create your own bidding algorithm, and you have to return a bid based on your own understanding of this bid request. And you need to develop a bidding algorithm that maximizes the object function, which is defined by adding all the clicks and conversions together. And conversions are apparently given different weights because they are more important. And all these will subject to the budget constraint. Of course, you cannot spend more than the money you have. The evaluation process of this competition is split into 3 different stages. The first one is the training stage. They give you the training data set. You use the training data set to develop your own model and test it. And then, on a daily basis, they update the daily ranks. They update the rank based on the test data set. Well, this data set is not given in the beginning, but you can actually see it when the daily rank updates. And finally, they have a how to test data set, which gives it the final ranks. You see, there's a hidden test data set, which has the chance of overfitting, which we will see very soon. For the data set itself, there are 4 types of different logs. These logs are bid logs, impression logs, click logs, and conversions logs. Unfortunately, there's no log for the user segments, user activities around the verb. There's no log for the user navigation, after the click, but before the conversion, right? And these logs include very many different fields, like the standard ones, like the time step and the verb page, URL, and ad slot. It also has some interesting ones, like the ad slot visibility. You can see there's a 16. There is an ad slot visibility. It says the second wheel. It means this ad slot exists not on the first screen. You have to scroll down to see this ad slot. Okay? It also plays an important part in the whole model. There are also user tags. The last one, the 24, the user tags. These are user interest segments. Basically, they say this user is interested in buying something. This user is interested in travel. This user is interested in reading. But unfortunately, we don't know what these numbers really represents. So we don't have any correlation between them, and we don't know the hierarchical structure of it. All right? Another 2 fields, the 20, bidding price, 753. This is a price you submit. In the log, it means from history, advertiser submitted this price, trying to win this impression. And the 21, the paying price, is defined by the second price auction. It means this advertiser has won an impression, and this impression was won at the price of 15. It's usually substantially lower than the bid price. Okay? And based on these data sets, we have all, the number of bids and impressions and clicks and conversions. There are normal figures like the click-through rate. Normally they are around 1%, or usually less than 1% and above 5%. But there are also interesting ones, like there is a conversion rate, you can see. There is a 55% conversion rate. That's very high. And by the way, they define the conversion rate to be the number of conversions divided by the number of clicks, not by the number of impressions. All right? Yes, please.
But how do you define a conversion?
The conversion is usually defined as a purchase of something or the download of the software. It's the ultimate commercial goal you would like the user to accomplish.
But how do you explain now that some sites have a 0% conversion rate, so absolutely nothing, or beyond the precision here, and others have 55%?
Yes, it's based on different definition of the conversion. You see, these belong to different advertisers. These advertisers are not shown here, but they belong to different verticals or categories. Some of them are like the travel, like the online e-marketers. And some of them are like very difficult ones, like the financial services. And you can imagine, for example, for financial services, it's really difficult for people to register a form and complete something. But probably for online shopping, it's much easier, like purchase something. Right? These are just the different characteristics of the advertisers.
Also, I know the company that I'm working with, the advertiser is free to define a conversion to be whatever they want. Mm-hmm. And it might be like they just land on some other page. So they don't have to buy anything. If the advertiser wants to, they can just say, oh, if this one visits this page, then we'll call that a conversion.
Mm-hmm. So the advertiser report on the conversion rate?
I'm sorry?
Who reports on the conversion rate?
It works like this. The advertiser, they have a web page and expect a user to visit. Usually they embed a small script on the final conversion page. And this script belongs to the DSP platform. That script will be triggered when user reaches that page and will be attributed as one conversion.
Right, but that's in the publisher website.
In the advertiser website. The user has already clicked, right?
Yeah.
Okay.
So if he chooses, he can, make 100% conversion rate if he wants.
Yes, theoretically, yes.
It's his signal.
No, I understand, but he can do whatever he wants with that.
Yes,
yeah.
Yes, that's true. Okay.
One question if we're here. Do you have logs for non-winning bids or just for the winning bids?
The winning bids is defined as impressions.
Yes.
And the bidding activity is defined by bids. And that's the bid requests.
Do you have logs for that too?
Or just let me answer you this way. We know which auction we lose, but we don't know why we lose it. You see?
Which auction, so for every participant in the auction, you have some log record?
If we have the impression, there's an ID of the bid of the auction ID, right? If we win this auction, we will have an impression.
Yes.
And we will have the paying price, knowing how much we have paid. But if we lose it, we have no log for the loss. But we know we lost. We know we lose.
You participated?
Yes.
Okay.
Yes. Okay. These are the overviews or the statistics of the data sets. And based on these data sets, the computation was divided firstly into two stages. The first one is an offline stage. Well, let me talk about the solutions of the offline stage first. With the training data set, we broke our offline bidding algorithm or the engine into mainly 4 parts. The first one is trying to extract the features. Second one is a click-through rate prediction. Third part, the whitelist revision. And the fourth part is the more subtle revision of the final bids. And after all these 4 steps, we give a bid for one impression. The first part is about features. We first, you see, there, from the log format, you already see there are 24 different fields. And based on these fields, we extract the first order features as well as the second order features by giving the combination of 2 first order features. And of course, we remove some meaningless ones, like you can't give hour equals to 8 and hour equals to 9 together. It's just meaningless. And we have around 700,000 features in total at last. This is the first step. And for the second step, click-through rate prediction, we used a very basic logistic regression model and with some cross-entropy training object and L2 regularization, and we implement this in Java. this is very basic logistic regression without any fancy modification. And the third one, for the click-through rate prediction model, we have to make it slightly complicated because you are not supposed to bid too high because the click-through rate is predicted to be high, and you have to cap your bid based on the click-through rate prediction, right? This is a method we try to modify the bid based on the CTR prediction as well as applying a cap. Okay, these parameters are learned empirically from the training data set. And actually, in the third season, we also talked to the organizer of the competition, and we also talked to other teams of during the conversation, we learned a lot about these parameters. Especially, there is you can see it's an exponential parameter. That A. We learned a lot from other teams. This, using the click-through rate prediction alone with a capping, give us rank 5. And you can see the curve, this bidding function, it gives a curve of a convex. But the question is the convex shape correct or not? This bidding function, that top right corner, is totally based on our intuition, right? It's not based on theoretical development. We want to understand, is this convex shape correct or not? This is exactly the part that inspired us for the third part of work. Okay?
Could you just say again how those A, B, C, D parameters were?
They were learned from the training data set. We just do a grid search, right? But especially for this parameter A, it's very difficult to, even for the grid search, it takes a lot of computation power.
When you say they learned from the training data set, you mean learn to maximize that initial objective that you talked about, the sum of clicks plus
yes, precisely.
I see.
Okay. And based on this bidding function, this is the first step. We already have a bid, right? That's B over there. We already have a bid, but this is not very satisfying.
Can you go back one time?
Okay.
How do you come up with this formula?
As I said, this is totally based on intuition. We want to build we know that if the predicted click-through rate is high, we should bid higher. And if it's low, we should bid lower, right? And there should be a relationship based on the prediction. And we also know that it can't be too high and it can't be too low. That's why we're capping it.
No, I'm just wondering, why are you multiplying by the base CTR? Okay. So it's
sorry.
I'm just saying. I'm just asking the y0 after, like, you're multiplying your click prediction, the squash click prediction, divided by the base CTR with the base CTR. With y0. We can talk about that later.
Okay. Yes.
Another question. How granular is that model in that, like, is that a global model that you fit for all advertisers?
Yes. Actually, in the training data set, there's only one advertiser. Or you are talking about different features?
No, because you have several advertisers with very different characteristics on your page.
Actually, in the training data set, there is only one advertiser. And I will talk about that later in the online stage. And online stage, they challenged us by giving different multiple advertisers without giving the corresponding training data set. Okay.
That's real life.
Okay. After the first stage, we won the rank 5, and we don't think it's enough, so we introduced some revision. The first revision is based on the whitelist. A whitelist is, it's based on the human understanding of rules. For example, from the statistics of the training data set, we already spotted some at slot giving very high performance. We can bid as high as possible. And this whitelist is purely constructed from the training data set, but there's one thing worth mentioning, which is the matrix, the performance matrix. In the second season, we used the wrong performance matrix, which is totally based on the predicted click-through rate. But in the third season, we used the high ROI, which is cost per click, or the clicks divided by cost. This gives the significant improvement, which give us a lesson, say the correct performance matrix is really important, okay? This finally gives us rank 3. And we still think this is not enough because some features are actually more significantly important than the logistic regression model says. And it's probably due to the overfitting problem, or it's probably due to the model itself, right? For example, we try to do something more subtle. Instead of bidding as high as possible with a fixed value, we are trying to do something more subtle, like if the advertiser is someone, sorry, this is a poor example. As I said, there's only one advertiser. But if the ad visibility is something, we multiply the bid by some factor. Okay? This is still mined from the training data set. It's a post-adjustment we try to impose on the bid itself. And this gives us rank 2. And at the end of the offline stage, we actually received the first place. This gives us some lessons, like you cannot overfit. If you overfit, like the guy did for the who won the first place, before the final rank, he overfitted and he received a slightly less score compared with us. Okay. And the second lesson learned from the offline stage is we need to use the correct matrix, which is we believe to be the effective cost per click instead of the click-through rate. All right? I will show you how this influenced out in the online stage. But before I talk about the online stage itself, there are some statistics of the online stage. As I said, there are 4 different advertisers, and this is the first challenge. And the second challenge is there were no logs. You don't have any log about it. No bid logs, no impression logs, no click logs, and no conversion logs. All right? But the good thing is there was no competition among 5 participating teams. They selected 5 teams into the online stage, and they claim there's no competition among us. Okay? How did they manage to do that? After the competition, they disclosed how they did the selection. When an ad request comes in, they first ask all the teams to generate a bid. But this is just a test. It doesn't count as a bid request. Okay? They ask each team to generate a bid, and they check if the bid is higher than the reserve price. The reserve price is a minimum price you have to beat if you want to win the auction. If your bid didn't beat the reserve price, you will not be able to participate in the final random choice. Okay? They finally random choose a bidder from the remaining teams. And you can see it is certainly biased because some teams are generally giving lower bids, which are much lower than the reserve price. If it's not biased, these teams will simply be able to bid but lose. But now this bidding opportunity was given to other teams. All right? In the online stage, our solution is basically the same.
Sorry, yeah. I think you missed it. Why are you saying it is biased?
It is biased because some teams will generally give the bid even lower than the reserve price because they didn't consider this factor. It is likely that they didn't consider this factor and they just give a bid lower than the reserve price. And if it's not biased, they will be able to see this bid request, or they will be able to have a bid request and just lose it. All right? But with this selection, they will not be able to see this bid request that could belong to them. And this request will simply be given to other bidders, given to other teams. I will show you how this bias is in the final statistics, okay? But let's come back to our solution. Our solution is simply modifying the bidding function based on the offline stage with the revisions and with the CTR prediction. And an interesting factor is a parameter E, which is modified for each advertiser. That's the only thing we can do because there's no training data for each advertiser. And we have to adjust this factor E dynamically during the online stage as the competition proceeds. All right? And we used the remaining budget and eCPC as the main factor we monitor during the online stage. All right? And we created a simple monitoring interface in Python. From the plots, there are something we did during the online stage. All right? First, you can see in the beginning, we bid slightly higher. Then we kept reducing the bid because we want to make sure we don't deplete the budget too soon. All right? And then we gradually increase the bid price by adjusting the factor E to make sure we can, that we can win the majority of impressions, and our eCPC is within our targeted range. Not a targeted range, but within a preferable range, as low as possible. And we also want to make sure we can deplete the budget, although we failed. You see, at the end, we only spent 75 yuan in RMB, but we were given 100. Okay. Generally speaking, our tuning was trying to win as many impressions as possible and not deplete the budget too soon or too late. All right. You can see from the plot there are vertical lines, and each vertical line indicates a change of the parameters. And this is for a single advertiser, and actually for other advertisers, it's more dense.
So what was the method of changing this? The vertical lines is changing the E parameter?
Yes.
What was the logic that changed it?
The logic of changing the parameter E is, as I said in the figure, we try to maintain a preferable eCPC, the cost per click value, which we consider to be the major performance matrix or the indicator. And we don't want to deplete the budget too soon or too late.
By preferable, you mean as low as possible?
Yes, as low as possible, while winning a lot of impressions. It's because there's no log. We only have the statistics, which is given every 15 minutes. And this competition lasts 2 hours or so. So you see, we can't adjust as frequently as possible, nor we can't learn, what's going on over there. Okay? Yes.
So you had they kind of publish different parts of the training data, and then you adjust the E parameter every.
No, they didn't give the training data. They didn't give the log level data. They only gave the data, as you can see from the plot. The number of impressions you have won, and number of bids you have auctions you have participated in, and your remaining budget, and your average cost, something like that.
They give that every day, and every day
Every 15 minutes.
I see.
Every 15 minutes, and yeah. Okay. And the online stage, it turns out, by using the correct metric, the effective cost per click, we won the competition, and we won 30% better than second place. Well, I think this basically because we tried to spend as much as possible, and we intentionally kept this eCPC low. By talking to other teams after the competition, we learned some of them simply use the linear function of the predicted click-through rate, and some of them, even simpler than that. All right, and probably they used it. You can imagine by using a linear function of predicted click-through rate, it's a wrong matrix, right? And even something even simpler than that won't give you a better result. So, just to review a little bit, what are the lessons learned from both the second and third season? As I talked a lot, you see, the click-through rate or the conversion rate prediction is not enough. All simple variations, the linear or the exponential form, is not enough. And by adding the budget constraint is still not enough, right? The availability and the win rate, or using the industrial term, it's a bid landscape, it must be considered, right? That's why we try to win the majority of impressions, not the majority, but as many impressions as possible, and while considering the eCPC. But you have to understand, we did that totally manually in the competition because there's no feedback. There's no log level feedback. And our ultimate goal is actually trying to develop a model that takes into account these factors and be able to do that automatically. All right? And note that the availability and the win rate could be dynamic, right? It could be influenced by the supply fluctuation and market competition. And actually, I skipped one slide here, which is, during the online competition for one advertiser, even though we increased the bid a lot, gradually a lot, in the past hour, we can't win more impressions because the market is also increasing the bid, or simply because there are not many impressions available there, right? It could happen. So you have to take that into consideration. Well, I'll stop for now and hand the controller to Weinan, who will talk about the third part, the theoretical model and solutions we developed based on our experience from this competition. Yeah, sure.
What kind of data size are we talking about here?
I'm sorry?
So the training data that you got for this competition, how much data are we talking about? Are we talking about megabytes, gigabytes, terabytes?
35 megabytes.
Gigabytes.
35 gigabytes. Sorry.
Makes a slight difference, yeah.
Okay.
Okay, thanks. All right, as Fry showed that we have a lot of considerations during our competition, such as the function form of the bidding function and the whitelist and also the final bidding revision. So all these are actually decided manually by some heuristics. So we actually, after the competition, we want to develop kind of framework or theory to automatically learn the optimal bidding function. We just directly from the data. So here, in this section, we will propose our bid optimization framework and the solution of the bidding function and this experiment and some future. So actually, in this real-time bidding ecosystem, we will now focus on the demand-side platform perspective. That is, you will receive a bid request and also the user data from outside the world, and you will need to return the bid response. That is a bid price for this impression, and you will connect the user feedback afterwards. And so the problem objective will be just as Fry mentioned in the competition. That is, you given a bidding strategy, by tuning the bidding strategy, you want to maximize the campaign level key performance indicator. That could be the campaigns achieved a clicks number or conversion number. And the constraint would be the campaign's cost should be lower than the preset budget. And this is just an abstract optimization framework. And before showing the formula, we should introduce some components here. So each bid request are formalized as a long high dimension vector here, including the user add features. And based on the input features, we can have an evaluation function about the KPI brings from these bid request opportunities, such as the CTR or CVR. So theta here means the CTR or CVR of the bid request X. And based on that, we can have a bidding function that is based on maybe the CTR of this bid request and also some features of the X. We will return a bid price. We will return the bid price of this case. And based on for this bid request, and we return this bid price, there is a winning probability function, that is the winning rate, I just mentioned, we should consider in the framework. So these are the optimization formulas we want to actually use. Actually, we also simplify our model by some dependency assumption. That is, first is we can directly evaluate the key performance indicator, that is a reward bring from this request, how much it can reward you if you win this auction. And based on this reward and also the campaign level bid landscape, that is how much you could pay if you bid this bid price. And then you can determine the bid price you want to respond for this auction. And based on that, based on the bid landscape, you will know the winning rate because you already know how much you bid and the bid landscape of this campaign. So you want to maximize. So here we can use we want to maximize the campaign levels total click number. So here NT means the campaign's expected auction number during its lifetime T, and for each opportunity, we consider that the bid request feature is generated from an identical independent distribution and with this probability density function. And based on that, we evaluate its CTR here and performs the bid and gives the winning rate based on this bid. So that's the probability of winning an impression. And times the CTR here, we will have the expected click number of the campaign level. And also, similarly, the cost.
You're running over all possible functions or over parameters?
So currently, as you see, we haven't defined the form of the function.
Oh, okay.
So this is actually a function optimization framework. What you want to optimize is a function, and you want to tune is the form of the function. And also, similarly, the cost will be like this. And here, the bidding price, we use the bidding price as a cost upper bound because it is normally a second price. But we not just use the second price because first is the second price is not easy to estimate, and the second one is, the price, the auction reserve price will always push the reserve price next to between the first price and second price, and very close to the first price actually. So based on that, and we also, here actually has some notations of this optimization function. And based on this optimization, we can actually simplify it because since we have already the CTR estimation function, we can directly simplify this integral based on the substitution methods of integration. We only integrate on the CTR of the x here. So we integrate the CTR here and have the simplified bidding optimization framework. And the solution will be based on the calculus of variation because what we want to optimize, what we want to tune is a function. So here's the Lagrangian the Lagrangian formula of this optimization, and take the Lagrangian functional derivatives with respect to the bid price and set it to 0. We can have the Euler Lagrangian condition of this solution. So please look at this function here, this formula here. As we can see, this is an condition of finding the best bidding function, the optimal bidding function here. We can see that actually the probability density function has already been erased because two of these have the same term here. So actually, in this condition, what we care about is a form of the winning function here. That is, given this bid, how likely the advertiser will win this auction. So if we have if we have known the form of the W function here, you can directly derive the function of your bidding strategy. So what's the shape of the winning function here? We directly learn it from the data. So here are the 6 campaigns in this in the IPO data set. As we can see that all the x-axis is the campaign's bid, and the y is the winning rate if the campaign bids with this value. So you could see that like that. The winning rate has a concave form with respect to the bid. The winning rate will increase dramatically at the very beginning and finally converge to 1. So with such observations, we can propose some winning functions, and based on that formula, condition formula, we can directly derive our bidding function. So first, the winning function will be like this. We can just model it using bid price over C plus bid price, where the C parameter can be learned from the data, from the training data. And based on that, you can see that the optimal derived bidding function is like this. It is actually a square root form. It is a concave form with respect to the KPI here. So actually, in our computation, we have derived a very first convex and then concave form with respect to the bid price, and along with a lot of whitelist and the bid revision rules. So here is this bid strategy is quite clear. And we can only change the winning function for different campaigns. If this campaign will have such kind of winning function, such as if this campaign are a little competitive and it has the bid will not increase dramatically at the very beginning, only after maybe 10 bid over 10 it will increase dramatically. We model the function, if we model the winning function like this and learn the same parameter using the data, we can also have our bidding function. So different winning functions will lead to different bidding functions. So in these two cases, the bidding functions are all in a concave form with respect to the predicted CTR here. So we want to make analysis here, compared to the linear bidding form. Our bidding form will allocate more budget from this area to this area. That is, the linear form bid will bid more than ours when the estimated CTR is very high, and we will allocate more budget, we will bid more. We want to win more about the cheap and low bids, with low bids. So actually, since the winning probability function is in concave form, so when the bid is already lower, if you increase a little bit of your bid, you will earn a large winning rate increase. But when the bid is already high, you will only earn very little winning rate increase. So this actually is very consistent with what we learned from the online competition of IPO, because when the bid is already lower, if you just bid like this, maybe it will not even surpass the reserve price, and you will lose this bid opportunity. But we can earn it by increasing the bid at the very beginning. So we use competition data set for evaluation, and the evaluated strategy will be constant bidding, which is normally used in sponsor search, and random bidding, and also the max CPC, that is, advertisers have the previous CPC target. You shouldn't earn a higher CPC than this kind of CPC. That is, you can learn you can regard the eCPC in the previous data set as the advertiser's private value, and you just bid based on the true value times the predicted CTR. And then the last comparator is a linear platform, linear form bidding function, and we have our two bidding functions based on our two winning functions proposed.
Question?
Yeah.
I think I missed your definition of eCPC and why you can infer the advertiser's private value using any simple heuristic.
Okay, that is if you served as a bid optimization framework, so what you should do is you try to lower the eCPC before your optimization, right?
And eCPC stands for?
Effective cost per click. It is normally used, it could be also called CPC, cost per click, but since the display advertising is always charged by CPM, so we actually use effective here, the term here, effective CPC. So
right, that's what
so
pay,
before,
but this is not how much the advertiser values that click.
You are the advertiser.
so for example, if you before the bid optimization, you will spend maybe $1 to earn each click. We want to by optimization your bid, you can spend just $0.8 for earn one click. So just like that. So also the test evaluation flow will be based on the data set. The data is a row per record. Each record has a bid request features and the auction winning price, and also the user's feedback on the ad impressions shown. And each time we send the bid request to our bidding engine with a different bidding strategy, that is bidding algorithm. And the bidding algorithm will respond to the bid price for this bid request. And the auction, the testing environment will do the auction, that is to check whether your bid is actually higher than the logged winning price of that auction. If so, this advertiser wins this ad impression, and the user's feedback that is already logged in the history data will be retrieved to see whether the user clicked this ad or even convert. And the result will be returned to the bidding engine. The test will end if there is no test data more, or maybe the budget has already run out. So the performance is like this. So here the 1/6 means that we just set the budget of the test as 1/6 of the original total spend of the test log, because we cannot set the budget higher or equal than to the original cost in the test data, because if so, we can just bid as much as possible in every cases, and we can earn all the click without spending all the budget. So with such limited budget condition, we can see that our real-time bidding algorithm actually outperforms the other algorithms. And also, this is a configure of clicks. And also, compare the eCPC here, that how much you spend to earn each click, you can see that we also have the lowest eCPC. And we can also set another KPI in your optimization. Say if you set a conversion number as your optimizing objective, then you can still have the similar result. And when the budget got increased from 1/6 to 1/16, you could see that actually the improvement got lower. But here we can actually have an analysis about budget here. Actually, you could see that when the budget is very limited compared to the original cost, you can see that the improvement of our algorithm against the linear bidding form is actually quite large. But when the budget goes higher and higher, there's more and more budget, the increase should be lower and lower. And of course, when we have the 1 point here, there is no improvement, because you just bid as much as possible will be okay. So here, when the budget is quite lower, we can actually spend more budget on the cheap cases, because cheap cases is always cost effective, because the other market will always concentrate on some high performance, high quality advertise opportunity here. So the future work will be, we will just try to expand our assumption. That is, we want to, such as the bid landscape will be depends on the feature of X, such as the time feature or location feature. And also we want to use the exploitation strategies during our bid to connect the data, because everyone knows that only if you bid high, you can have the ad impression, and then you can train your data. If you lose, you cannot know what the user will feedback. So this is a biased training situation in display advertising and also sponsored search. And also we will try to look at the roadblocks. That is, you will try to buy several combinatorial ad slots in one page view, because if this page was dominated by your ads, actually some analytics say that this advertising performance will be even higher than the sum of the individual ad impression. And also we will look at the dynamic aspect of the bidding, that is the changing of the market price and also the user's click model, which to balance the reward and the uncertainty of your advertising performance. So risk-aware bidding strategy will be another very important research topic later. Okay, thanks. Thanks.
Any other questions? Yes.
Yeah, I have. So you started to present that you can either model based on CTR or based on conversions, but at the end, through all reasoning, you are more focused, obviously, in clicks, right?
Yeah, here in our setting, we mainly care about clicks, but of course you can care about the conversion.
Because one of the problems problems with conversions is that you even have less training data.
Yes. The conversion is even sparse than click. So, and also different advertisers will have different conversion definition. So here we mainly study the clicks.
And second question is the user features. So do you think that it would be also useful to use the semantic neighborhood between, so statistical semantically twins between users, clusters of users based on browsing history? Because in the beginning the example was that you were searching for booking hotels, and then you were saying that behavioral targeting is more important than contextual.
Yeah.
But at the end, if you actually don't know what is the semantic, the interests of the user, it doesn't really matter for your bidding function, right?
You mean the semantic between the context and your
User
ads?
interests, let's say.
Sorry?
The user interests.
The user interest. Okay, so actually in each DSP, in each demand-side platform, we actually implicitly do the user segmentation. So only actually say if you like ad science, this is a user segmentation. But actually you like if this page if this ad is about general research, you actually have the the semantic relevance, right? But currently. In this current platform, we don't use the user segmentation, just the user. We don't use the semantic relevance, just the user segmentation, directly match. Okay. Yes, that's a good question.
Great. Edit, please.
Yeah, related to the question on the clicks, I know in our company the advertisers complain that although the algorithm buys lots of clicks, they say, it buys lots of cheap clicks, and these cheap clicks are really crappy clicks because they're not clicks that lead to conversions and so on. So we look at like these sort of bounce rates as well, like these non-bounce clicks or sort of quality clicks. But I was wondering whether in your framework you have anything kind of you could say about the quality aspect of buying lots of clicks?
Not really. This framework, actually it takes any kind of feedback or matrix at the object you want to optimize. The only reason we use the click is in the computation it is click. And especially in the search season, the weight for the conversion is 1. It means the conversion is equally important as the click.
Oh, right.
So that's why we followed that tradition and use that in the model, because clicks are easier to understand, and it removes the sparse observation problem. But the model itself can take any kind of feedback as the object. And actually, in the paper, we also evaluated the combination of clicks and conversions. You can give conversions a very high weight. Right? In the beginning, you don't have any conversions at all, but the clicks plays as the object. Then you have several conversions which plays a more important role naturally in the model itself.
So here the framework is trying to optimize the campaigns levels, KPI. Actually, you can define the KPI. What is the KPI? It could be the impression number plus click number, and the conversion number. You can define it yourself.
More questions?
One last question. And you don't model your competitors in this framework. So what I'm asking is, because I know from some friends that they say that there are some patterns where the cost of the bidding cost depends also on time, on day of the week, on day of the month, because they receive a budget, they have lots of money to spend, and they just spend. And even some companies spend the money at every 30 minutes. They spend more money every 30 minutes than on the other time. So do you think in future work to consider also these?
Yes, that's totally true, and that's probably the most important part of the future work. It's a first one of the future work. While the market competition leads to the different bid landscape distribution. If the competition is high, you will win less, even if you bid high, right? That's what we call the bid landscape. And at the moment, in this framework, we assume this bid landscape is static, and it totally depends on how much you bid, and it has nothing to do with the market, outside market. But you know, the future work will be doing that dynamically and consider the competition and probably, you know, add some decay factor to it, because you know the recent information is more valuable.
In the data set that you used here, would you have information on those kinds of dynamics? Do you have any information on how maybe your competitors have changed over time?
This relates to the very first question I got asked. We don't have the negative, you know, sample all the auctions we lost.
But
Right.
you don't know when you lost?
We know we lose, but we don't know who win it and how much he won it.
You know how much
Wait,
you
if it's a
pay.
second price auction, you still have an increase in your winning price over the time of the, towards times of higher competition. I would expect.
Assuming the same bid.
I mean, if you always place the same bid and the market gets denser, your winning price will go up.
Yeah.
Right. So you would even see it in the winning price.
But you know, the impression level winning price will be missed because this is the only chance you cannot get back. Sorry?
For the cases where you win, you will know the winning price,
Yes, that's true.
Yeah.
so you can get some information from it.
Yes, of course. That's true. That's part of the information we can have from the second price auction. Yes.
Okay.
You assumed a functional form for the win rate, and then you derived the bidding rule from the equation, from the differential equation. Is that right?
Yeah.
If you do what you're suggesting there, learn the win rate function empirically, is it easy then to turn that function into? Do you mean to learn that empirically? Do you mean still some kind of fixed functional form, or what do you mean?
Why we use this kind of winning function is because we notice that the data is look like this. The winning probability is in a concave form. Then we derive two kinds of winning functions here. And of course, if for some campaigns, maybe the winning function is different, and you can propose different winning function formula. Actually, this is an open module in our framework.
Yes, from the last slide, you can see the shape of the actual winning function is not very complicated. And you can always find a curve that fits to it very nicely, and you only need to learn the parameters. But the problem is this curve changes over time.
This is a dynamic. This is a dynamic bidding landscape.
You said per winning function per campaign. Is the campaign the right way to slice that?
So for each campaign, you have the target rule, right? You have a target rule, and then you will have, you will receive the bid request which matches your target rule. Yeah, and the other one. Will you try our bidding function in your platform?
Well, it's certainly.
I would like to know
Yes.
I can tell you that this looks a lot better than what we're doing currently.
Thanks very much.
Because currently, it's just a linear. Basically, just
you use a linear
just
function.
a linear function of the predicted CTR or predicted conversion rate.
Okay.
Looking at when they compare those, the linear function looks pretty good compared to
Pretty
the
good job.
random.
Yeah,
So linear
it's not bad.
It's simple and give good results.
It's not bad.
Can you set the budget quite limited?
Sorry.
Can you set the budget quite limited? You just use a very limited budget to do the comparison.
Yes.
Okay.
More questions? Okay, no more. Well, thank you very much. Thank
Thank
you,
you.
Brian. Thank you.